Hello everyone, welcome at the second day of Unite with sessions. My name is Sven, and today I'll be talking about extending the animation rigging package with C#. I'm a graphics developer in the R&D team based here in Copenhagen, but for the past year I've been working on the animation rigging package. So in this talk we'll take an in-depth look at what you can do with the animation rigging package. Yesterday Dave already gave a great talk about the things you can do with the animation rigging package. But in this talk, we'll take an in-depth look and try to extend the animation rigging package with our own custom constraints. So before we get started writing our own custom constraints, I would like to take a bit of a step back and have some background information about the animation rigging package to make sure that we all have a solid foundation to work from. So we created the animation rigging package to suit all your rigging needs inside Unity, inside the editor. Currently, there's two main workflows. We supply runtime rigging, so we allow you to use the runtime rigging, animation rigging framework to do runtime animation in your gameplay. Also, we allow you to do animation altering inside the editor by making use of the animation rigging framework during preview in the animation window and timeline. The animation rigging package has been in preview since 2019.1, so you can install it in any project from this version onwards through the package manager. I must warn you though, the package is still in preview, so the code is likely to change as we add more features to the package. However, the exciting part is that you can help us drive development of the package. We want to make sure that along every step of the way, that the package supplies the functionality you need it to do, and we stay true to your projects. So the core design philosophy we had when designing the package was to be modular and extendable. We did not want to have a solution that just works on your humanoid character, where you have 2 arms and 2 legs. Instead, we want a framework that works for all your characters, so also your fantasy characters that have wings, arms, or tails. But we took it a step further than this, and you can also apply the animation rigging framework to your environment pieces and vehicles. Basically to anything that makes use of the animator component. So let's take a look at what it takes to set it up. We start out with a character that is animated using a few clips for its animation. To this, we add our rig builder and a number of rigs. The rig builder just takes care of setting up the framework, and the rig is just a container to hold any number of rig constraints. Under your rigs, you add any number of rig constraints that you need for your setup. These rig constraints contain your normal transform constraints, but also contain a set of inverse kinematic constraints. If you're familiar with digital content creation tools, you'll probably be familiar with these constraints as well. So in the package, we supply 11 constraints out of the box. For each of the constraints, there's an example you can obtain through the package manager, and there's a scene that explains how the constraint works. So by setting up your constraints, you can create procedural motion at runtime or alter new animations inside your animation window, because the constraints create a rule set how the animation should move. So since the rig constraints, this is the place where the magic happens. So let's talk a bit more about this. Inside the package, we have 3 types of constraints. The first type of constraint I would like to point out is world interaction. This type of constraint generally contains some form of inverse kinematics and is great to make your character interact with the game world. So it looks much better when your hands actually touch the surface of the table instead of penetrating through it. So overall, your character will be much better integrated inside the game. So in this example over here, we can see the pink scorpion, which is our base animation. To the tail of the scorpion, we add the chain IK constraint. This allows us to correct the end position of the tail and make it attack the actual ball. This looks much more aggressive for the scorpion and much more realistic. Next to world interactions, we have a constraint that I will call procedurally secondary animation. This type of constraint generally contains some sort of physics-based simulation or time-based simulation. A great example of this constraint is a damp transform constraint inside the package. So on the left here, we can see that only the sphere is animated. And following the sphere, there's a chain of cubes. By adding the damp transform to every element in the chain, we get this nice, smooth-looking motion in the chain. So then the final constraint category I would like to point out is your skeletal deformation fix-ups. You can use this to make your skinning look much better and create high-end skinning characters. So a great example of this is your normal twist bones. So we have our upper arm and lower arm bone to control the pose. But to this, we add secondary leaf bones that act as twist bones to control the skinning. In the example here, I'll show you to you. You have to look at the upper arm and you'll notice the difference. So all the examples I've shown you so far just contain a single constraint active at a time. And there's a great deal you can do with this, but there's much more you can do by combining your constraints as you like. So to set up more constraints, you can group constraints under your rig transform. As these constraints might rely on each other for execution, it's important to think about the execution order of your constraints. The package collects the constraints in a depth-first approach. So that means that damp1 will always execute before damp2 or any of the other constraints. Basically like this. And just like you're used to the hierarchy, this works with childed game objects as well, below your rig transform. So this is just a single constraint at a time. But in this example, we'll have a look at the possibilities you can get where you have multiple constraints active at the same time. So in the example over here in the background, we can see the ninja character playing a single idle animation. All the animations on this slide build up this single idle animation. The only difference is that we add various constraints to our ninja character. And we keyframe the properties in a different way. So here we have the ninja idle animation playing, and we created this staff idle animation by just adding constraints. There's no different animation, but we can take it much further. For example, as Dave showed yesterday, we can have the ninja eating ramen in Mega City. But we can also have ninja looking out over Mega City. Do some sword fighting practice on the rooftops of Mega City, or just hang around. This, by just adding constraints, we can create really versatile animations. And these animations don't have to be saved to a new clip. You can just change this and keep this inside your scene. We're basically reusing existing motion that's already present in our base idle animation. So I promised you to get a bit more technical, so let's talk about that. The animation rigging framework is built upon the Playables API. The Playable API is used for the evaluation of data sources in a tree-like structure. So inside Unity, you'll commonly use this for your audio and animation systems. Inside the Playable API, you have animation C# jobs. And in the framework, every rig constraint is its own animation C# job. These C# jobs allow you to execute a game or your rig constraint inside the animated thread. So you can modify the pose before it's written back to the scene. And furthermore, it allows for easy multi-threaded code because the animator takes care of scheduling the jobs for you. Because we're running multi-threaded code, we cannot simply access our transforms inside the scene anymore. Instead, we have to make use of the animation stream and stream handles. The stream handles allow us to extract data from the stream. We cannot directly access the data from the stream because the data might be in a different place in the stream from one place to the next. So this is what the animation rigging framework is built upon. Inside the animation rigging framework, we provide additional wrappers around these stream handles. So instead of a transform stream handle, we have a read-write transform handle. Likewise, we have a read-only transform handle. But in order to create properties in there, such as weight, we also support your primitive types inside the stream. And also we have the normal vector variations you're used to and quaternions. So using this, you can extract and put data into the stream. There's only a bit more code you need to access the data. You cannot access the data directly. So let's take a step back, and I want to point out that we designed it to be an open rigging toolkit. That means that all the constraints I've shown you are available in the package. You can just open the package folder and look at the source code of every single constraint. But you cannot only look at the source code, you can modify the source code as well. And in the package, we've even taken this a step further and allow you to write your own custom constraints. The constraints supplied in the package can get you a very long way, as you've shown you in the examples. However, there might be cases where this is not enough and you want to have completely unique behavior. In this case, you might want to consider writing a custom constraint. Likewise, if you're squeezed for performance, you might want to write your own custom constraints because it allows you to take everything out you don't need. So it just does what you need it to do. So let's get started by looking at some code. Every rig constraint inherits from the rig constraint class. The class itself doesn't do much, but in order to be a rig constraint, we need 3 parts. First of all, we need to declare a job. This is our I-weighted animation job on which we implement our algorithm for a rig constraint. This is also the job that is executed on the animated thread. Secondly, we need to define the data our job is going to work on. This supplies all the necessary data we need to execute our job successfully. And then finally, our third component is the animation job binder, which takes care of creating and destroying the job. So that's all it takes to implement your own custom rig constraint. The system will hook the rest up for you. To illustrate, or to go through the steps on building your own custom constraint, we came up with the simplest constraint possible. It's just one line of code. We take the position of one transform, multiply it by -1, and write it to another transform. So in the example over here, the user is moving the blue cube. When the blue cube gets moved, we take its position, multiply it by -1, and write it to the red sphere, which is our constraint object. So, as I said, the first step we do is implement our rig constraint class. This is what it looks like for a Hello World example if we have the 3 components already declared. So let's have a look at what those 3 components are and how we declare them. The first thing we need to define is our Hello World job. For this, we need an I-weighted animation job, which in turn implements an I animation job. The I animation job is part of the Playables API and allows us to build an animation job. And our interface only has a single float property, which is the weight value. This value is automatically populated by the system, but it's up to the developer to implement this inside the algorithm of their constraint. I would strongly encourage every developer to implement this inside your algorithm, as it will make your animations look much better. In this example over here on the left, you can see the 2-bone IK on the arm being blended in and out. Whereas on the right, you have a hard switch between the constraint being on and off. The popping will really stand out in your game. So blending allows the animator to smoothly enable and disable constraints. Every constraint we supply in the package supports the blending of the weight values of the constraint. So let's have a look at what the Hello World job looks like. Here we can see the code for a Hello World job. At the top, we have our 2 transform handles. Below that, we have our job weight property. And then there's the process root motion function. You don't have to pay much attention to this, and we only need to implement this to be a valid animation job. The system we don't make use of this in the animation rigging framework. Below that, we have our process animation. This is where we get to work on our algorithm. The function gets passed in the animation stream we're working with. So the first line, we're extracting the job weight from the stream. Then in the if statement, we check if our weight value is larger than 0. If it's larger than 0, it means that we have some actual work to do. So in the line below that, it's the same line as mathematics I had on my slides before. The only difference is now that we're using our handles and we're interpolating the new position, so the position multiplied by -1, and the old position according to the weight value. So we get proper weight blending. And just like any other job, we can further optimize its execution using burst at the very top of the code. So now we have our job. The next step is to define our data. In order to do this, we need to implement the iAnimation job data interface. This interface has two functions. The first function returns a Boolean to notify us whether the data is valid to build a animation job. And the second function resets the data back to the default values. So let's have a look at what the implementation looks like. As expected, in our data definition, we have our two transform variables. And we say the data to be valid if we have both transforms assigned. Then when we reset it back to its default values, we set both fields back to null. So with those two components defined, we have done the most difficult part. The only thing now is we need to connect them up in a job binder. So to make a job binder, we need to inherit from the animation job binder class. This class has three functions. First, the create function to create the job given its data. The destroy function takes care of destroying the job, and there's an update function that allows you to update the job from the main thread given the latest data that was available for the next frame of execution. So our implementation is much simpler than the class I showed you before for the animation job binder, because the only thing we need to do is we need to create the job. When we create the job, we bind the handles to the transforms in our data. And on the destroy function, we don't need to do anything because we did not allocate any memory or use any native arrays. Also, we're not making use of the update function because our constraint is super simple. So this is what we end up with. On the left, you can see the component you can add in the inspector in your rig hierarchy. Just to reiterate on this, the constraint doesn't execute on the main loop. Everything you see happens on the animated thread inside the job. The component you see here on the left is solely used for the artist to set up the parameters and serialize the data. So in other words, it doesn't impact your main loop. As a developer, the framework should allow you to focus on writing your custom constraints, not on writing the boilerplate code that is needed for parallel evaluation. So with those steps I've shown you, that's all it takes to start writing your own rig constraint job. And at any point, you can look at the code of the existing constraints if you want to have more examples. But to give you a better understanding of what the framework does behind the scenes, I came up with this simple example. Over here, we can see some programmer animation. We're making use of the same idle animation we've seen before. But on top of this, we use a single rig with three constraints. We use one constraint to control the left arm. Then we use our hello world constraint we just created to copy our left hand position to our right hand. And then we apply 2.ik on the right arm. This allows us to get the mirroring clapping motion. So in here we can see our state machine as well. It's really simple, just a single idle animation. So as I mentioned before, the animation rigging framework is built upon the Playables API. And the Playables API comes with this great debug tool called the Playable Graph Visualizer, which can be obtained through the package manager. Once you've installed this successfully in your project, you can open it through the analysis submenu under the window menu. When we open this up, over here. So when we open this up, the first graph we'll see is the result of our state machine. This contains your animation clips, animation mixers, and layer mixers. And the lines we can see connecting the nodes is our animation stream. Just so it's clear, this graph reads from right to left. So on the far left for you, we can see the animation output. This is our final result of our state machine. And the white line you see is the animation stream and can be considered as an animation pose flowing through the various nodes, where every node might do an operation on this pose. But it's not just only the animation pose. The animation stream also contains a custom flow data you might have defined in your animation clips or anywhere else. So if you have a look at the top left, there's a drop-down where you can find other playable graphs. So our animation rigging framework acts as a post-process on the state machine graph from before. So when we switch to our animation rigging playable graph, this is the graph we get for a simple clapping animation. We have the previous values from our state machine are being fed into this graph and then flow down to all the layers. Every layer will have its own horizontal line. So in this case, we have our rig 1 we're using at the very bottom. And our final pose is available at the bottom left. So if we were to duplicate our rig, we get this example, and we can see that our rig created another layer that has the same style. And again, our animation stream flows from our state machine graph into the first layer above and flows down through the graph. This gives us our stack-based evaluation we need to solve the dependencies between our constraints. So in this case, rig 1 is at the very top in our rig builder. So this rig gets executed before the second rig, which is the final rig we execute to get the pose. So let's go back to our simplified example, and let's dig a bit deeper to see how the animation script nodes map exactly to the constraints we have. So in our rig hierarchy, we have two game objects. We have our left arm to control the left arm, and we have our right arm. On the left arm game object, we have two constraints. Our left arm IK, the 2-bone IK, and our hello world constraint to copy the data from the left arm to the right arm. So the left 2-bone IK is the first component on our game object. So this is the first node that gets executed. Then we run our hello world constraint to copy our data from left to right. And finally, the right arm game object is lower in the hierarchy, so this gets executed after that, at the very end, as a final node before we reach our animation output at the bottom left. So one thing I've been ignoring in these slides is this guy up there. So I want to talk about this a little bit. This is the first layer that gets executed before anything else gets executed. And this layer is not the result of any user setup. Rather, it's something that's built by the system to make sure that everything works as expected. The task of this layer is to push the latest scene data into the stream. Because this layer gets fed the state machine data from the previous playable graph, not all the latest scene data might be available in the stream. But we only want to do this if those values are not animated by the state machine. So inside the framework, we made sure that it's super simple to do this. The way you do this is to flag your fields on your data with the sync scene to stream attribute. But not only, so we already used this in our hello world data constraint. Our hello world data constraint did not make use of any animation. The only input we had was the user dragging the cube around in the scene. So our source object, we need to inject the latest scene values into the stream in order to get the proper evaluation we desire for our constraint. But not only we have this attribute, we also have a rig transform component that allows you to quickly update and inject a game object transform into the stream. So you can simply add this component to any transform in your hierarchy, and the system will pick it up and make sure that the transform values are available inside the stream. So this example over here illustrates how this works. This example has 2-bone IK on both of the legs, and the effectors of this 2-bone IK are parented below a game object. This game object is not part of the animation stream. So now we can see that our 2-bone IK individually works properly. But when we move this intermediate game object, the execution doesn't happen as we expected. And this is because it's not evaluated in the animation stream. So when we add the rig transform component, we make sure that this intermediate game object is part of the animation stream, and the evaluation happens as expected. So I might have lost some people with these last few slides, but I want to make sure, there's one thing I want to make sure. You need to make sure that the latest data is available inside the animation stream. You can do this with the sync scene to stream attribute or the rig transform component for your transform data. So Now, I've taught you how to use the animation rigging package to write your custom constraints, and we had a look behind the scenes at what's going on. The only thing you need now to be successful is some imagination. So, to spark your animation, I would like to go over the concepts on how you'd go to writing about a custom jiggle constraint like this. So let's get a more serious image of this jiggle constraint, and we'll take this as an example. Our jiggle constraint should work on a chain of any length. But to simplify our explanation, we'll just take our root and tip transform. Our algorithm will easily generalize to a chain of any length and to the 3D, like the slides are just 2D. So let's take this as our starting frame. This is the place where we build our job. So the jiggle constraint works by doing a form of particle simulation inside the animation job. For this, we need two positions. We have our target root position, which is just simply our tip position. Then the second position we need is our target. And this target gets set up from the root to our tip, this direction, we extrude the target position along a distance we call the dynamic offset. This is just an artist parameter your artist can use to create different looking jiggle effects. So now that we have those two positions, we can initialize our particle at the target position. And then on this particle, we can do this particle has various physics properties, such as mass, position, and velocity. So now let's have a look at what our constraint looks like during runtime. So let's say in our next frame, our root and tip have been moved and translated. This in turn results in a new root target and target position. Our particle, however, is still in its old location. So now we have an interesting scenario where we can apply forces and constraints to our particle. So the first constraint we apply to get our jiggle effect is a constraint that pushes the particle away to its initial dynamic offset distance. The second constraint we apply pulls the particle back to the desired target location. And because we're in charge of the simulation, we can add any number of external forces. So for example, we can apply gravity or wind to our particle. So by taking those three components into account, we end up with a new particle position. And using this new particle position, we can create a new lookat vector for our tip transform. So our tip should always be looking at the particle's location. So we can calculate the delta rotation and just simply apply it. This creates the cool jiggle chain constraint we had on the slides before. There's only one problem. For our jiggle constraint to work, the particle needs to be translated. And there's a single case where this doesn't happen. When we rotate our root transform along the roll axis, our particles stay in place and the simulation doesn't run properly. But this problem can be easily solved. We can simply add another particle that is orthogonal to our first particle. And this also allows us to do the cool jiggle simulation on the roll axis. So here we can see our cool jiggle chain constraint also work on the roll axis. To put our jiggle constraint to the test, we've applied it to various assets from the Book of the Dead. So here we can see the jiggle constraint simulating a totally realistic looking tree. But since we accounted for external forces, we decided to apply it to our whole forest. And since we can apply wind sounds to it as well. So there's a big storm going on in this forest. And we even have applied our jiggle constraint to Ninja. Here we can see Ninja being tired from a whole day of playing around in Mega City. So unfortunately, we don't have time to go over all of the code inside the jiggle chain constraint, but the source code can be found on this QR code. There's also a bunch of parameters for the artist to play with. And everything that's involved inside the code for this Jiggle chain constraint is exactly the same as we used in our Hello World constraint. So feel free to use this code for writing your own custom constraints in your project. And please show off your amazing work with us. With this presentation, I hope to have given you a good understanding of how you can go about writing your own custom constraints. Also, I hope that the look behind the scenes was insightful. And with the Jiggle constraint, I hope to have sparked your imagination so you can come up with much more amazing constraints than I have done so far. So as I mentioned in my introduction, the animation rigging package is still in preview. So please get in touch with us and share your feedback with us on the animation rigging forum. Next to our Jiggle chain constraint, there's also the twist chain constraint source code available on the QR link on the bottom. So thank you. This was my presentation. Are there any questions?
Okay, it's not really that difficult of a question, but do you intend to support, I mean, there's 2D rigging now in Unity. Do you intend to support that specifically? I mean, it should probably work anyways, but are you going to add specific support to any of the 2D features?
So at the moment, there's the 2D rigging package, which allows you to do inverse kinematics. And our intent is that this package will merge with this package at some point. Currently, there's nothing stopping you from using the animation rigging on your 2D sprites and skeletons. The only thing is our constraints make use of factor 3s, and you probably only need factor 2 for 2D.
All right, thanks.
So quick question about the dots integration of this. So basically, is it already possible to run all this through the dots renderer, basically, to stay on ECS land?
So the playables API is not part of the dots framework. So this is the playables API is before that, and it's older than that. So it's not part of the dots framework at the moment, but with the dots animation coming up soon, we hope to migrate our runtime rigging package to dots animation as well, so you can stay in dots.
Okay, thank you.
Hi. So about the Jiggle chain constraint, I'm curious about if it's possible to every cube that you have in the chain, instead of driving that transform, can you drive actually another control in each cube? So if you move, if you rotate one control in the middle of the chain, you have the last part reacting as well, or you only can have like defining the head and the tip, and the rest in the middle is not actually animatable.
So in this example, the source code up here, I don't think this is the case, but you could customize it that it is the case. And in this case, you'd just be taking into the new positions you do from the scene.
Okay, thank you.
I actually have another one. How well does it integrate with physics?
So this is one challenge at the moment, and we experimented with this ourselves. But it's difficult to get data from the physics world into our animation job. So often when you do this, you'll get 1 frame delay, which might be sufficient in some cases. In other cases, you don't want to have this. And currently, the way, since we're in old Unity, it's hard to solve this. But when we move to dots, we hope to solve this problem more easily and have physics integrate well with your custom constraints.
Cool, thanks.
I actually also have another one. So things like this chain are usually pretty easy to do with like 5 elements or something. But once you reach like 100, you usually need to do like a back pass to like not make everything weird. So is that possible with the current animation constraint system, basically?
I'm not sure if I fully understand the question. The question is if we have a really long chain, you're likely to get instabilities?
Oh, usually if you have like a really long chain, you want to do this kind of forward pass that you're doing right now, basically taking the values from whatever element came before in the chain. But then you also want to do like a back pass, basically accessing like correcting
Mhm.
for the motion of
Yeah,
things later in the chain.
Yeah, so in this Jiggle constraint implementation, the whole chain is evaluated in one constraint. So inside your algorithm, you could write the code to do this backwards pass as well, or you could implement this in a separate job, which gets evaluated after your first rig constraint.
Okay,
That's
cool.
up to you. Okay, no more questions? Thank you.